device for measuring electric fields outside the lab and hold it like that. What do you think? Would there be anything to measure?
With or without the shielding?
A little bit.
No, with or without the shielding?
What do you mean without the shielding? There's no.
Okay, like
No, outside there is no shielding. In the sense that we were now in the shielded lab. Yeah. Okay, now we go out with the sensor for measuring electric field outside the building.
Yeah, there will be very small amounts, residual amounts from the AC distribution, or even the phones. You could find some. There are defined values of field strength in these areas, also for the industry and for the inhabited areas.
Telecoms. Good. Yeah, there are different reasons for that. There we have many sources of electric fields outside. Okay, I gave you that. Okay, but now we go, it's hard to find such a place in the Netherlands, to a place where there's no industry, no traffic, no nothing, nobody's living there. And we go there with our system. No trees.
So do we carry your cell phone with us?
Sorry? Okay, no cell phone. No sources, I said.
there will be.
Then it would be zero?
No.
No. What do you measure then?
The small electric.
Electric field between the Earth's surface and the clouds. Yeah. How much do you think would it be? How much of a field strength in volts per meter or kilovolts per millimeter on a relatively nice day like today? Any idea? Probably not. No, you can easily have 100 volts per meter, which sounds pretty dangerous, you know, for me being almost 2 meters, so 200 volt on me. But would that be the case? If that would be the case, it would not be safe for me outside. So, which mistake do I make here? In assuming that, okay, it's 200 volts, no, 100 volt per meter, let's say, you know, almost 2 meters, so that's 200 volt from those.
It's I think about the area, not the height.
Sorry?
It's about the area, not the height, like 200.
No, 2 meters. Anybody else? What do you think, Adela? That's a bit strange question. Yeah?
Insulated means we are wearing shoes that can insulate us from the ground. We cannot follow the path.
Oh, when you were getting there, where I want to go. Okay, but let's start with, okay, I don't have any shoes, I don't know why, but barefoot. So, now the next question is, what do you think? Am I an insulator? More like a conductor, 70% water, what is it? So I'm a conductor. So that means that I will change the electric field that's present there due to my presence. So I'm going to lose a lot of time, but I think it's important that we that's why I'm certainly going to lose a lot of time. No, it's right. Yes. Earth's surface. Okay. I make myself very simple. This is me. Without me, there's kind of a uniform electric field, 100 volt per meter, and you have the equipotential lines, let's say, with equipotential lines that are going like this. Oh, it's supposed to be parallel, but yeah. Now there's me coming there. What would happen? Something like this. They would go around me because I'm a conductor. I should be at the same potential as Earth. So equipotential lines have to go above me, meaning that I'm field in which I am standing is very, very small because it was reduced by my presence. Yeah. Now you with your insulating shoes. There's that. Okay. So I will not be necessarily on at the same potential as Earth, but still I'm conducting, which means there can be no electric field inside me. Therefore, so that wouldn't help too much. Of course, there are situations, but I will tell you more about that later when the lightning storms. The electric field is much higher than other things. Okay. But I will tell you about that much later, a few weeks from now. So that was a question. We still didn't answer that question of mine. Would we measure something? Okay, yeah. Maybe something that gets close to 100 volt per meters, not exactly, because also with our measuring device we will disturb the electric field distribution. You always have to think of that if you measure any parameter, that by introducing a sensor or measuring device, you may very well change the thing you want to measure, in general. Okay, the other question was why? So we had this round, we had this plate here, Y, and the voltage here. Why we have a higher electric field than here? Fringing, yeah, okay. So fringing is a word. Yeah, it's the thing that's happening there, but why is it happening there? And what is it?
Maybe because there is more charge. Actually, the charge tend to gather in the sharp actually areas of the metal or conductors.
You're getting very close there. We know that here in we have a certain let's say D. Oh, here, let's take it here. D vector, and D really is epsilon E, and really is the amount of charge on the electrode divided by the surface area on which it is. So if there was very small surface area, so at an edge here outwards, we have a high charge density, and thus we have a high value of D and high value of E. But this is still, you can also get to the answer by making a drawing. So now I will already spend a few minutes of time on a topic that was supposed to be presented next week. I argue that by the knowledge you have now, you could already, by making a drawing and pen and paper, you could already get to the answer. I'm going to increase the size of the okay. We're going to draw in equipotential lines. You know what they are, yeah? Lines of equipotential. And we are going to draw here field lines. You know what field lines are, yeah? The field lines, we know that they end perpendicular to the electrodes. Yeah. So here it's simple. Here it will have to end perpendicular, and here as well. What do you think? Is there a reason why? Could it be something like this? There's no real reason, so okay. Forget about that. We have a straight line. Straight line, easy enough. Straight line. Straight line. In real life, we do not have infinitely thin plates, so I'm going to draw a small radius of curvature. Okay. Okay. The field line here would have to start perpendicular here, and then where would it go? Curve down, yeah. And here and one. Also have to go. Forget about the rounded roof after that. Yeah. Okay. Okay, it should be something like this. So how can this help us? Okay, now we draw equipotential lines. Maybe one halfway. This one. Be perpendicular here. So we have to move upwards a little bit here.
Okay.
It's easy. But now I take one, this is maybe 50% time, I take let's say 90% of the voltage is here. Okay. And another one. Okay. Now we know that the distance between equipotential lines is a measure for the magnitude of electric field. See where I'm going at? It should look here. They're much closer, the equipotential lines, than they are here. Because they are moved, they are pushed upwards. Yeah? And so at the same time, of course, here the field is getting smaller. Yeah? This is a kind of proof just by using the knowledge that this knowledge. Yeah? Nothing fancy about that, but it's quite smart because not only this configuration you can approach in this way, but many others, all configurations, in fact. So you don't need to know much. In fact. Don't worry, you still have to learn many things, but with this knowledge you can do a lot. If you forget about the computer, the lab manager spoke about, we'll speak about it next time. But just with the pen and paper, if you understand basics, you can solve the problem. Okay. Yeah.
The same thing happens at the other corner as well, right?
Yeah. This is symmetrical. Yeah.
Okay. But why is it that when the voltage at the center is less and towards the ground it's more?
No, I'm not sure if I understand what you're saying now.
When voltage was measured at the center.
Here?
Yeah.
Yeah.
Towards the upside. No,
Yeah.
I mean to say towards the plate. Towards the plate in the center.
Towards the plate in the center. Yeah, here. Yeah.
When the voltage was measured here, it was less, and the
Less than what? Less than here.
yes.
Yeah, but look at the picture. Yeah.
Why was it?
Okay, look, this is let's say the 90% of the voltage. Let's say the 90 volt line. Yeah. We keep at the same height with our measuring instrument. We go out. Maybe say, then we have our sensor here. Yeah. Yeah. Same height. Yeah. Okay. This is now not 90, but maybe this is 85. Yeah. But the electric field is this potential minus this potential divided by distance from speaking. Yeah. So across the same distance now, we have more voltage, so higher field. Yeah.
Is there any approach to definite the exact amount of electric field at the edge of the actually this plate, except of the sensors? I mean, the theoretical approach.
So can you repeat that? I missed part of it.
I mean, is there any theoretical approach to definite and to certain the amount of electric field at the edge of the plate?
No, the original exact method is not applicable here because the exact method was only applicable, let's say, the parallel plate, infinity parallel plates, right in the middle. There, the exact method is can be used, but not there. And that's the whole point. Yeah. In fact, I can even argue that by this very simple method, if you draw this to scale, yeah, measuring device. And pay attention to how you draw things and know the voltage. You draw your lines, maybe you have some iterations because this is for sure not 90 degrees, so I made a mistake. You have some iterations until you have perfectly 9 degrees. Then you use your measuring device and say, okay, we know this is 80 volts, 100 volts. I measure the distance, and you have the electric field, which is an approximation. But then what you can do is, okay, I will draw some more equal potential lines here, and then the solution becomes more precise. Yeah. Now I take this difference in potential divided by that distance. So it's really amazing how far you can get. I should not be carried away, but you can in fact here. Okay. That's the beauty of I think of such a simple approach. If you know what you're doing, you can do a lot. Okay. But now I really have to move on. Otherwise, we need to have extra lectures. I don't want that. So these are the reasons for again summarizing why we want to be able to calculate multiple layers. Yeah? Because we can have some air gap or cavity due to faulty production and so on. Okay. The next step, we can have exactly the same approach. I will go faster now through this because it's the same approach if we have coaxial cylinders. Again, we apply a voltage on the inner conductor, 0 volt on the outer conductor, that's coaxial. Then, of course, we have a charge Q on the inner conductor. And what we do is we take a closed surface around this inner conductor so that it contains the charge. So what we do is you see the dotted lines there in the picture. So we choose a cylinder with a radius in between the inner and the outer conductor. And inside this cylinder is the charge Q. Yeah? For instance, we take the cylinder at the distance x. And then we can say, again, we have the integration there. We get d times d. In which direction is d, in fact, here? Outside, radial, yeah? And we assume that, because we have to talk about infinitely long cylinders, so we assume that the cylinder doesn't stop here at the left of the so it goes on. Then we take a chunk of the cylinder here. So we only have a d if this is the cable that goes radially outside. Yeah? So we have to multiply d with the area through which d is flowing, so to speak. Yeah? What is the area of a cylinder? It is there, but so it's the circumference of the cylinder, which is 2 pi x, 2 pi r if you like, times the length of the cylinder. Yeah. That's what you see there. Okay, then you can calculate E. E is then Q divided by 2 pi epsilon L x. Then we integrate between the boundary conditions. And finally, we get a well-known relation for the electric field in a cable geometry, a voltage cable. There's a logarithm inside. Yeah? So this is not a uniform field like in the parallel plate capacitor anymore. You see that? Where's the field highest in this construction?
Surface.
Which surface?
In a cylinder.
In a cylinder, yeah? So the smallest radius of curvature is also what we say, yeah? Because at the inner and outer cylinder you have the same amount of charge, yeah? But polarity is different. Do you realize that? This is just a capacitor, yeah, but it's a bit different than a parallel plate capacitor. One plate of the capacitor is plus Q, the other minus Q. Here is exactly the same. Yeah? But in the inner cylinder conductor, the Q is distributed across a much smaller surface area than the outer conductor. So at the inner cylinder, Q Q divided by A, which is really D, the flux density, is much larger than at the outer cylinder. And if D is much larger, E is also much larger. I can understand if you cannot follow my reasoning that fast, but some of you can, I see that, so recheck before we have the next lecture.
Can you just say again what L is?
L is the length of the cylinder, we take a certain length of the cylinder.
Then we integrate on a volume and not on a surface anymore, is it?
No. We would integrate across the volume if we would have taken the surface area of this surface area, which is pi r squared. Yeah, but we took 2 pi. Yeah. Don't make that mistake. I'm not saying this to you, but to many, because it happens too often that this is mixed, and then of course you get it wrong. Okay, that's for a high voltage cable situation. There you go. So we already reasoned that we will have the maximum field at the inner conductor. Yeah? Now it's easy enough to calculate this maximum field. You can see here we just take for the variable x small r, which is the inner radius, and that's then the maximum electric field situation. We can also calculate now the capacitance here, this piece of cable, which makes sense also in real life to know the capacitance of a high voltage cable, because it's Q divided by U, very simple, and there you see now the capacitance of a piece of cable of length L, inner radius small r, outer radius big R. Very simple. For those of you who are working at a cable manufacturer, not all of you, but you have to make these calculations. What is the capacitance of your cable? And those of you using the cables in the network should also know what is the capacitance, because if you have too much capacitance in your power system, you may be into trouble. Huh? You have to compensate that with inductors. Okay. Suppose that, okay, we are dealing with a fixed outer radius of the cable, yeah? And we are allowed to change the radius of the inner conductor. Then you can imagine that there would be an optimum radius of the inner conductor where we would have the minimum electric field possible at the inner conductor. Right? Can you understand that? For certain voltage that you use, that makes sense. So what is the situation? This one is fixed. R. And this one is not fixed. We can choose small r. Let's look at it in very simple manner first. Now that you can all see it. If there's a fixed voltage drop across, so that we cannot change. Now if we take a very small inner radius, we have a large insulation gap. Yeah? So you can argue, oh, maybe we have a low electric field then. Yeah? It's very simple thinking, I agree. Yeah? But at the same time, we have something with a very small radius of curvature there, so a very high field concentration here. So it goes in the other way. We can also reason, no, we want to have as uniform an electric field as possible, because that's always the optimum. I haven't said that yet, I've said it now. So we make it larger, much larger, like this, but then we have a very short insulation distance. So probably there's an optimum somewhere in between where we have a minimum field. Stuff's not good for my voice, as you can hear that. So how to find out what is the best? It's very simple technique you should all know. We're going to differentiate E to this variable. And we say, okay, that should be 0, because then we either have a minimum or maximum. Yeah, we take that operation, and then you can find that the optimum value for, still the other way around, right? See that? No, sorry, forget about that thing. The optimum value for the inner radius is outer radius divided by E, with E being 2.7 something. Yeah. And the optimum electric field, we can also calculate now, in fact, is E times load voltage divided by the outer radius. This is something that is being used in practice. Makes sense, because we always want to keep the field as low as possible. Or why would we want that? I'm making these bold statements every once in a while, but why? Why do we want to keep the electric field in a real construction such as high voltage cable as low as possible if we can? To avoid breakdown, because the higher the electric field, the higher the electric stress in the material, so more aging and so on, weaker. But there's also another reason, that suppose that in a situation where we have a really high field in the insulation, there's also a cavity, manufacturing defect, gas filled cavity. Well, then we're in bad shape there, because one, the electric field will be enhanced with a certain factor. Let's say for now, the factor is epsilon. Yeah. For polyethylene, high voltage cable, epsilon is 2.3. So we would have an electric field which is already high, enhanced by a factor of 2.3 in a medium that is very weak. So, if we can, we want to keep the electric field low, and to come back to what I said before, as uniform as possible. That's another piece of information I give to you. As uniform as possible, what does it mean? That it's the same everywhere? Yeah, it's the optimum situation. Why is that the optimum situation? I'm throwing this information at you, but you are never allowed to just believe what I'm saying because it's me saying it, or because it's in the book. No? Well, maybe it's a bit tough to understand right now. But let's say we have insulation between my hands, yeah, and you can see this piece of insulation as a stretch of many small parts of the same material. Yeah. In order for this system to break down, only one part has to break down. In fact, in a high voltage cable, hundreds of kilometers, sometimes only in one location, something has to go wrong, and then you have your breakdown. And I often use the analogy of a chain with different links. Yeah. What determines the strength of a chain? The weakest link. Yeah. So it doesn't make sense to make a very strong chain and one link is weak. It's throwing away money. Yeah. So the optimum is where all the pieces of the chain are equally strong, so a uniform strength. Yeah, this is what is behind. Okay. This is again the same story, but then when we have different layers of material, dielectrics in the cable. Apart from the fact that maybe we could have a delamination, which is one layer, which is a slip of air. In which case can we expect different dielectrics in a cable like this? Any idea? In a normal cable, we'll have only one insulating material. But then you have cable terminations where they end. I can tell you very often there you have two different insulating materials. I will get back to that later. Yeah. So it has relevance. You, yeah.
When we saw in the cross section of a overhead cable, for example, we saw a lot of different layers.
Okay. I need to correct something here. When I speak about cable, I mean something that's underground. I haven't said this here, so always. What you are talking about are overhead lines. When I say a line that is a thing that is not insulated, well, it is insulated by air. So I'm not considering that. Yeah. Okay. So you can do the math yourself now. In this case, I will not explain this. It's the same story. Concentric spheres, again, same type of calculation, but who cares if we have no practical use of this equation here at the bottom? Who cares? Now let's have a look at the photograph there. What is that? Exotic high voltage thing there. This transformer in a few sections on top of each other. What is there at the top? It's like a magnification of the eye of a fly. Yeah? See the segments. This is a big round thing. You believe at the top there we have the highest voltage. Yeah? So we don't want to have any sharp edges there, because sharp edges means small radius of curvature, means very high field. Yeah? So we need to have something that makes the top, where we have the highest voltage, nice and smooth and large and round, not sharp. So in the old days we used one blown aluminum body, but it's very expensive to produce a body like that. It's very smooth. So here we approach smooth body. If you close half your eyes, you see only one smooth thing here, yeah, from a distance. But this makes much more sense. This is the thing consists of different elements. So if by accident some of them are damaged, you can just replace this one single element. You don't have to replace the whole thing. That's what we used to do. So you could argue, yeah, but there are all these hollow areas in between these elements. Doesn't that give any problems? Yeah. Think about it. I will get back to that also. Yeah. But that's not the reason why this picture is here, obviously. It looks a bit like a sphere, doesn't it? That thing. I can imagine many things here. I can be in high voltage technology. You need to be very, very creative in imagining things. But we make many simplifications. But as long as you know what you are doing, you are relatively safe. So the top thing I tell you now, because you don't believe me otherwise, we consider like a sphere. So where's the other sphere? We're talking about concentric spheres. And now I will ask even more of your imagination. The building, yes. It's weird. Huh? So we have an inner sphere and an outer sphere, because we want to have some easy way or very quick calculation of the electric field at the surface of this sphere. Because of course we don't want to have any breakdown there during testing. And we know roughly the size of our lab, height, and then we can calculate the electric field we have for a certain voltage and certain inner radius. That's a segmented thing. The outer radius is really the lab. Isn't that nice? It's an approximation, of course, but it gives you order of magnitude at least, and you get a little bit closer. So one of the things I could ask during the exam is, okay, please design a high voltage lab for me that, no, I'm not joking, simple high voltage lab for me, in which we can do testing with 1.2 million volt AC without having flashover to the roof and everything all the time. How would you approach that? It's easy enough to say, okay, I'll use my laptop and I will program this in my field calculation program. Well, it's not so easy, in fact. Okay, you see, you have to use your imagination, but you have to know how much you imagine, yeah? Because there's an end to what you can, what is allowed. Also, for concentric spheres, there's an optimum there. Suppose that the outer radius is fixed. The problem is with the high voltage lab, we cannot just increase and decrease the size. So that's a fixed size, and you want to know what is the optimum value of the inner radius of the segmented part given a certain voltage. And you do the same calculation, and the optimized electric field is 2 times the voltage divided by the inner radius. Or the optimized radius of the segmented part there is half the radius of the lab. So there are some students that calculate, okay, we have a lab of 25 meters height, so it's roughly 12 meters radius. So this thing should have a radius of 6 meters. You must be joking. That's the optimum value. Of what we're looking for is the value of the radius where we don't have any problems. Yeah? And that means that we should have a radius where the electric field is below which value? We don't want that breakdown in the air. What was the value? No idea. No?
3 kilowatts per millimeter.
Around 3 kilovolt per millimeter. We want to be on the safe side, so we say let's say 1 kilovolt per millimeter. Yeah? So you also have to be a little bit smarter than only knowing that, okay, we take half the radius of the lab. Yeah? That's the message here. There's another example of the use of concentric spheres, which is nice. GIS system, a glass insulated system. Have you seen it standing in our lab, in the right and the back? Otherwise, have a look there. So there are these pipes, concentric pipes. You see one horizontal, one vertical. Evidently here we need to go around the corner. And the corner is just the thing. We can now, for a fixed outer radius, for the horizontal and for the vertical part, we can now calculate what is the optimal radius of the inner conductor. Yeah? It's outer conductor divided by, yeah? But now for where we go around the corner, looks to be quite a sharp edge. It's like a knee. Yeah? It's the knee of the system. Yeah? And the knee, okay, we can simplify that by assuming that it's also a kind of a sphere. Also, your knee is also kind of, you can see that as a kind of a sphere. Yeah? So then we need an outer sphere. So evidently we need to do something to the knee in the GIS system. So it's rounded off a little bit. And now again we can calculate the optimum value of the inner radius, the sphere part inside, as a function of the outer part. Yeah. It's again, of course, this is simplification, but I can tell you it's being used. Okay. Also here, if you want, you can easily calculate now the capacitance between the two spheres. That's important. This here, you cannot read that. They tell you when they teach you as a teacher that if they cannot read it, don't show it. But this is a page in the book which gives you an overview of 3 situations: plate, cylinders, and spheres, of the electric fields, potential distribution, capacitance, and so on. Yeah? So you have everything together. Yeah? I think it's time, over time. Okay. So I went a bit slower than I wanted to, but I hope the time I used was well spent and that you understand that you should understand. Okay. So see you again next week. Enjoy your evening. Yeah? Don't put the character between two insulating layers. No, this is showing that this is something that will go wrong. This is meant to show you what happens if you have misfortune.
Oh my God! My bus will be late.
What it is, what the illumination is.
I got to the field.
You made a video.
This is paper and plastic. This is laminate on top. Yeah.
It's amazing.
The whole like
What's in
this. Maybe inclusions. That's that each of them is air in between. In the real high voltage performance, because the temperature changes, we get mechanical